Good afternoon, students. Okay, last week we have seen the definition of linear transformation. On that, we have seen the problems regarding of the linear transformation. So I have told two definitions. So any one definition you can use and you can solve the theorems and also problems. Okay. So in that unit only, that is the fourth unit about the linear transformation. Next we have the fifth unit is there. That is a matrix of linear transformation. So in that you have the definition of what is one-to-one mapping and also onto what is onto mapping and also what we call those names of one and also onto. Okay, what is bijection? I have told bijection means one and onto both together. It is called as a bijection. Okay, see the definition of the what is monomorphism, epimorphism, and also isomorphism. Okay, these we'll use in the theorem, solving of the theorem. So if you know the concept of what are the definitions of these three, then you can do the problems and also the theorems. Okay, so in that, so if we have let v comma w be two vector spaces over a field f and v to w, that is a mapping from v to w, be a linear transformation. LT I am writing in the short form, that is LT is the linear transformation, then T is called first one epimorphism, monomorphism, a monomorphism if T is 1. Okay, if the mapping is a 1 mapping, then we call it the T. What is a T? T is a linear transformation. Then we call the transformation as a monomorphism. Okay, and we call it as an epimorphism. If T is onto. Okay, so if it is onto, then we call it as an epimorphism. Third one is isomorphism. This third one is important one. And isomorphism if T is bijection, we can call it as a bijection or we can call it as 1 and onto. If T is a bijection, that is or you can write in brackets, that is 1 and onto. Okay, so these three are important. What we call it as a monomorphism and what we call it as epimorphism or else isomorphism. So 1-to-1 relation, if it is satisfying, then we call it as a monomorphism. If it is onto means epimorphism. And third one is both. Combination of these two is called as isomorphism. So that is 1 and onto, or else it is called as even bijection also. Okay. So one more thing is, in this only we'll see about the concept of the linear operator. Linear operator means whenever the two here vector spaces are there, no, if these two vector spaces instead of two, one on itself only. So V to V. So it means one and itself. One and itself we call it as a linear operator. So V to V to, so from V to V itself. That is on whatever the transformation is there in between of the one vector space only. If you are doing the transformation, then we call it as a linear operator. Okay, so this is also important one. A linear transformation of a vector space V into itself is called a linear operator. On V That is, its notation will be like this. T mapping from V to V. Okay. So some problems he will ask to find the linear operator means whatever the vector space is there, if it is mapping onto itself, then we call it as a linear operator. Okay. And one theorem is there in your textbook regarding of the inverse of the linear transformation. That is the important one. For the section B, you will get for 10 marks question, that one. So when we can find the inverse of a linear transformation. So for that, the condition is that when T is a bijection, then we can find the inverse of the transformation. If T is a transformation, if it is satisfying the condition of 1, 1 and on to, then we can find the T inverse of that transformation. Okay, that is the inverse transformation. For that one theorem, whatever the theorem statement is there, if you remember that statement, with the help of that, we can find the inverse of the linear transformation. It is, let V comma W be two B2 vector spaces over a field F and T belongs to homomorphism of V comma W. Okay. Then T is invertible, then T is invertible means we can find the inverse of that one. Invertible. You know, this is the symbol for if and only if. So T is invertible if and only if T is a bijection. T is a bijection. Okay. That means if T is satisfying 1, 1 and on to condition, then we can find the inverse of the T. Okay. So here T belongs to homomorphism of comma W. So there is a relation between that one. When we call homomorphism means if two vector spaces are doing the transformation over the same field F, means for V also the field is F and for W also the field is F, then we can tell that it is the homomorphism of V comma W. So the set homo of V comma W is a vector space over F. This homomorphism of V comma W means it is the, that means V comma W are the two vector spaces over the field F, over the same field F. Okay. So on this, whatever the invertible you have, on this you have one problem is there. That problem you will get for 5 marks question. Means one transformation will be given and transformation is defined. So defined means first thing, the transformation is from R2 to R3 or R3 to R3. It may be the mapping. After that, the T, whatever it is given T will be there. It is defined in some way. So if by using that definition, we have to find the inverse of the transformation. So in the question, it will give to find a T inverse. So to find a T inverse, what are the conditions? It should be 1, 1 and on to. Bijection in the sense, we have to show the relation, whatever the definition of T given in the question, the definition is satisfying the 1, 1 condition and on to condition. Okay. So for such type of problems, one more condition is there in your textbook. That is, if T is a 1, 1 condition, whether we can show that it is 1, 1 or else curl of T. Last week I have given the definition of curl. So if curl of that one is equals to 0, whether it is 1, 1 or curl of T equals to 0, then we can prove that it is a bijunction. Okay. That theorem also you have in your textbook, page number is in your textbook. It is their theorem. That theorem is also important. We have to show that alpha equals to beta. So that theorem you will get for 5 marks question. Page number 40, 52 page number it is. Exercise you have 5.4.2. Let V comma W be two vector spaces and T T is mapping from V to W be a linear transformation. Prove that T is 1, 1 if and only if curl T equals to 0. Okay. So to prove this theorem, we have to show that T is 1, 1. Okay. If and only if curl T equals to 0. That means 0 vector. If you prove that curl T is 0 vector, then it's enough that we can say T is 1, 1. It is satisfying the 1, 1 condition. Okay. So curl T value if we'll get as 0, then we can show that T is 1, 1. To prove that one problem is there. So with the help of that problem, you can solve. That is a invertible linear transformation. So we'll see that problem. Okay, problem is that prove that the mapping T R3 to R3. Okay. So that means in R3 you will have the 3 elements. R3 to 3 R3 defined by T of A comma B comma C is equals to 2A plus B comma B comma A minus B plus C. Okay, this is the definition of the T. See, this R3 to R3 means here 1, 2, 3. 3 elements are there. It is mapping to these R3 elements. This is 1, 2, 3. 3 elements. Okay. That is a definition of this one. Okay. So for all A comma B comma C belongs to R3 is invertible. So we have to show that this relation is invertible and we have to find T inverse. Okay. So to find T inverse, here invertible means it should be a bijunction. That means it should satisfy the condition of 1, 1 and on 2. Okay. So in this problem, whenever T is defined as the function to itself, here see T is a function. It is defining from R3 to R3. So here from 3 elements, whatever the elements are there in R3 are there and 3 elements means itself from here to here. V to V have told no linear operator. Similarly, if whenever the function is from itself, then we need not to show that it is a onto function. If we show it is 1, 1 function, it's enough. Then whatever the transformation is there, the transformation is invertible. Okay. So to show that, just now I have told one condition. That condition, with the help of that condition, you have to show that it is 1, 1. Okay. So to prove that T is invertible, this theorem is there. To prove that invertible, it is enough to show that T is 1, 1. Okay, T is 1, 1 or curl T equals to 0. Okay, this is the definition of kernel T. Okay, so if we show that kernel of T equals to 0 or T is 1, 1, then the given transformation T is invertible and we can find the T inverse. Okay, So from the definition of the kernel T. So kernel T definition is that kernel T equals to X such that X belongs to V, comma T of X equals to 0 dash. So this is the definition of kernel of T. Okay. So that means if you will get the element as a 0, then that is a kernel of the T. So then it will be automatically 112 function. So for that, choose that let A, here already A comma B comma C are there. So take that one only. Let A comma B comma C belongs to R3. Whatever there here, you are writing that one. Let A comma B comma C belongs to R3. And so whenever they belongs to R3, then the kernel of whatever T is there, that is T of A comma P comma C equals to 0. So this is the by the definition of kernel of T, we are writing this. So T of A comma B comma C. So what is T of A comma B comma C defined in the question? That value you have to write this one. That is implies 2A plus B comma B comma A minus B plus C is equals to. So here three elements are there. So 0 also you can write as 0 comma 0 comma 0. Now you equate these elements. So that is 2A plus B equals to 0. Second element B is equals to 0. Third element is A minus B plus C equals to 0. So now in the first one you substitute B value as 0, then you will get the A value. So if you take B as 0, 2A plus 0 equals to 0 implies A is also equals to 0. So here we got B equals to 0. Now A and B you substitute in third one. You can take like this. Okay. Now here A value is 0, B value is 0 plus C equals to 0. So implies C is equals to 0. So what we got? Therefore, A equals to B equals to C equals to 0. So we got all the whatever the elements are there, A comma B comma C, we got 0 comma 0 comma 0. So therefore, what is given in the solution, what we have written, to prove that T is invertible, it is enough to show that T is 1, 1 or kernel of T is equals to 0. So we got all the values of A, B, C as 0. So it is satisfying the condition of kernel of T. Okay. So therefore T is invertible. So we can write here, hence T is invertible. Okay. So it has the first if and only if it is given in the question, then we have to define it itself in two types. Okay. So here T is invertible. First one is completed and next one is fine. We have to find the T inverse. So to find the T inverse, now you take suppose. So T inverse means this is T. T is defined as T of A comma B comma C. Okay. So for that you take suppose T inverse of X comma Y comma Z equals to what are the values of T of that one? A comma B comma C. Okay. So if you'll take the inverse that side, what will happen? X comma Y comma Z. X comma Y comma Z is equals to T of A comma B comma C. Okay. So now this whatever X comma Y comma Z are there, these are the inverse values of T of A comma B comma C. Okay. So now we have to find the X, Y, Z values. So T of A comma B comma C. And what are the T of A comma B comma C in the given question? That is X comma Y comma Z is equals to 2A plus B comma B comma A minus B plus C. Okay. Now you equate the terms. That is first one is, okay. First one is here place will be not enough. I will write above. So 2A plus B equals to X, B is equals to Y, and last A minus B plus C equals to Z. Okay. So when you equate the terms, you will get it as 2a plus b is equals to x, then b is equals to y, a minus b plus c equals to z. Okay. So 2a is equals to x minus b. So what you get a value? A value is equals to x minus b by 2. And from here, what is b value? B value is y. Therefore, a is equals to x minus y by 2. Okay. Here b is equals to y. We got a value, b value. Now we need to find the c value. So first write a value. A is x minus y by 2 minus b minus y plus c is equals to z. Okay. You take z this side or else these terms to that side. So what you'll get? C is equal to z minus x minus y by 2. If this minus will go that side, it will become plus y. Okay. Now C is equals to z minus x minus y. This if you take that side, it is okay minus x. Minus of minus is plus y plus 2y. By this whole thing is 2. Okay. So this is, you can simplify this as so C is equals to, therefore C is equals to z minus, this is x plus 3y by 2. Okay. You can keep like this only or else you can split this one like this. T is equals to z minus x by 2. You can separate x and plus into minus is minus 3 by 2 into y. Minus term you keep like that only, x minus y. So what will you get? Minus y plus y. Minus 3 by 2. Okay. So this is minus for this term only, no? So minus x by 2. This is plus 3y by 2. Okay. Now we got therefore a is equals to x minus y by 2. B is equals to y. C is equals to z minus x by 2 plus 3 by 2 y. So here what is their inverse of? So T inverse of x comma y comma z is equals to a comma b comma c. So therefore we got a, b, c values. If you substitute here, that you will get it as an inverse of that one. So therefore T inverse of x comma y comma z is equals to, these all right in place of a, b, c, these values. That is x minus y by 2 by z minus x by 2 plus 3 by 2y. Okay. So this is the method how to find the inverse of a linear transformation or T inverse. Okay. Thing is you have to check whether the whatever the given transformation relation is there, no mapping. The vector space is from itself only, that is R3 to R3 or R2 to R2. Then we can find the, then it is enough to show that only whether it is a 1-1 function. So if it is from R3 to R2 or R2 to R3, Okay, this is a method how to find the inverse of a linear transformation. So next, we have to find the linear operator. On that, you will have one problem in the 6th unit. You have this concept. So these are the important questions in unit 5. Finding the T inverse. That is 52 page number. You have 5.4.2. This is the 5 marks question. Next 51 page number, 5.3.11. This is the important one. This you will get for 8 marks question. Next 5.3.9. This is also for 10 marks question. So section B you will have the 10 marks. No? So these all are the 10 marks question. Next 48 page number, you have the fundamental theorem of homomorphism of vector spaces. So I have told last week only that how you have solved for the fundamental theorem of homomorphism of groups and also rings. Similarly, you have for the vector space also. That is a page number 48. This is a very important one. So this is also 10 marks question in the section B. So from these three, so almost 3 8 marks questions are there, and these are the very regularly asked questions. And if you'll see, you'll have the 3 sets ABC. So from these 3 sets, any one, whichever set you will attempt for your examination, in that you may get any one question from these questions. Okay, so try to practice these all theorems. Just now what is invertible we have seen now. That theorem is here, it is showing that 1-1 condition and also on-to condition. And then we can show that it is a linear transformation, so that it can be done the inverse of that one, invertible. The condition is bijection we have to show. That is only showed in the theorem. Okay. Next we'll go, if we'll go to the unit 6, it is a matrix of a linear transformation. So in that one mapping will be given and also definition of the T will be given. We have to find the matrix form we have to find here. Okay. So with the help of that definition of T, and here 2 bases will be given in the question. With the help of that basis and also with the help of the definition of the T, we have to find the matrix form of the linear transformation. Okay. Matrix form, you know, no columns will be there and also rows will be there. So with the help of that, you have to find the matrix for the linear transformation. That's why the unit is matrix of a linear transformation. Okay. Unit 6 is matrix of a linear transformation. So when in the given question, T will be T mapping will be given and also T definition will be given with the help, and also basis. 2 bases will be given for the transformation T. So with the help of that, you have to find the matrix. So that matrix, again, if you do the converse of that one, you will get the again linear transformation definition. Okay. So we know already that column vector is called as a vector space. So we can write the vector space as the definition as the column vector, we call it. Okay. So in that we are almost in 6th unit, you have the problems will be there. So theorems are not there, but problems will be there. Sometimes these problems will be asked for 10 marks question in section B also. Okay. So first problem in that mapping will be there, definition will be there, and one or 2 bases will be given in the question. So with the help of those given data, how you have to find the matrix, it is the problem regarding of this question. Okay. So problem will be like this. Find T R3 to R3, R3 to R2. Okay, here itself is not there, from R3 to R2. Means in these 3 elements will be there in this two elements will be there. In the given definition also we can see defined by T of x comma y comma z equals to. So this is 1, 2, 3. Here 3 elements, no? So 3 elements are there. R2 means only 2 elements will be there. So x plus 2y comma y minus 2z. So this is the relation of T. Relative to basis. So here 2 bases will be given. Relative basis 1. One is B1 is equals to 1 comma 0 comma 0. Second one is 0 comma 2 comma 0. And third one is 0 comma. Okay, this is one basis. Next one is of R3. Okay, this is the basis for R3. Why? Because in this elements are three elements are there. 1, 2, 3. 1, 2, 3. And even the whatever the coordinates are there, those are also 3 coordinates are there. Okay. So next basis is B2 equals to 4 comma 0. Okay. See here, 2 coordinates are there, and in that the elements are two elements are there. Okay. So of R2. So why like this? Why? Because the given whatever the relation is there, T, it is R3 to R2. So these are 3 elements, these are 2 elements. Here, these are 3 elements, and whatever the points are there, the points are also 3. Here, two elements are there, and the coordinates are also 2 coordinates. Okay. So now we have to find the matrix of the linear transformation for this one. Find T R3 to R2 defined by this one. Okay. So now with the help of this basis, we have to find the relation of this one. Means here you can take it as a basis of B1 as small b1, b2, b3, and basis for b2 as c1 and c2. And these values you have to substitute here as x, y, z. Then you can get the values of T. So when you substitute these 3 elements here, you will get 3 different values. So with the help of that, you have to frame the matrix for the linear transformation. Okay. Now in the solution, you take, let B1 is equals to, here whatever the basis is there, that one as B1 comma B2 comma B3, and B2 is equals to, here already we have taken B, no, so we can take C1 comma C2. Okay. So this is B1, this is B2, this is B3, this is C1, and this is C2. Now P of B1. P of B1 means what is B1? That is T of 1 comma 0 comma 0. So T of 1 comma 0 comma 0 means this is x, this is y, this is z. Substitute here. So you'll get the value. So x value is 1. 1 plus y value is 0. So 1 plus 0. Y value is 0. Z value is, that is 2 into 0 means 0. So you'll get it as 1 comma 0. Okay. Next T of B2. Now what is B2? 0 comma. Now substitute there in the same relation only. So this is x is 0 plus 2 into 2. Okay. Comma. Y value is 2 minus z value is 0. 4 comma. This is 2 minus 2 into 0 means 0. This is 4 comma 2. Okay. Next T of B3. T of what is third one? 0 comma 0 comma 3. So x value is 0, y value is 0. Means this value whole thing will be 0. 0 comma 0 minus 2 into 3. It is equals to 0 comma 2 into 3 means minus 6. Okay. So third value is 0, comma minus 6. So now this is about R3. So from R3 to R2. R2 means here we are getting the B2 basis. So that you have as a relation 4, comma 0 and another one is 0, comma 5. So that you have to substitute and you have to find the matrix for this transformation. Okay. Now before problem we have done now like that only here let A comma B comma C belongs to R3. Here three elements are there. So B2 we are doing now. In B2 how many elements are there? Only two elements are there. Let A comma B belongs to R2 and A comma B. So up till here we have find the, with the help of this basis we have find the values of the T of that one. Next we have the second basis now. Second basis is let it is in the R2 form. So we are taking only A comma B. A comma B belongs to R2 and this A comma B we are defining it as A comma B equals to P into this one C1. Okay, we can write like this also. Plus Q into C2. So A comma B is equals to what is C1 value 4 comma 0 plus Q into C2 value is 0 comma 5. Okay. So when you multiply them, what you will get? This is 4P. This is 0. So only 4P comma and this is 5Q. So this A comma B equals to 4P comma 5Q. So when you equate these two values, so we'll get A is equals to 4P and B equals to 5Q. So in this relation, we need B and Q values, no? P and Q values. So therefore, P is equals to A by 4 and Q is equals to B by 5. Okay. So these are the values. With the help of this relation, we are finding P and Q values. So P and Q values are A by 4 and this is B by 5. When you substitute here, what will happen? So A comma B is equals to A by 4 into C1. What is C1? 4 comma 0 plus Q value B by 5 into 0 comma 5. Okay. Now with the help of this relation and then with the help of this one, we have to find the matrix of the linear transformation. So first thing is with the help of first basis, when you substitute here that basis values as B1 and B2 and B3, you will get this relation. With the help of this relation, you will get three values. One value is 1 comma 0, second value is this one, and third value is 0 comma minus 6. So with the help of this second basis, you are doing one relation. That relation is that A comma B is equals to P into the C1 plus Q into C2. So we need to find this P and Q values. So when you equate this, first you multiply them. After multiplying, if you equate A comma B on both sides, then you will get P and Q value. So whatever we have defined the relation, if you substitute, you will get this one. Okay. So now this relation and with the help of this relation, we have to find the matrix. So what is given relation? T of x comma y comma z equals to T of x comma y comma z is equals to x plus 2y comma y minus 2z. Okay. So now what is T of B1? T of B1 is equals to, so what we got B1 value 1 comma 0. So this value is 1 comma 0 is equals to, so you take instead of this relation A by 4 plus B by 5. So here A value is 1. This is considered as A and this is considered as B. Okay. So this relation and this relation. So A by 4. So A by 4 means here A value is 1. So 1 by 4 into 4 comma 0 plus B by 5. What is B value? 0 by 5 into 0 comma 5. Okay. Next second T of B2. So T of B2 is equals to, what is T of B2 value? 4 comma 2. So this is equals to A value is 4, 4 by 4, 4 comma 0 plus B value is 2. So 2 by 5, 0 comma 5. Okay. So here 4, 4 will get cancelled. It is 1 into 4 comma 0 plus 2 by 5 into 0 comma 5. The third one is T of B3. T of B3 equals to, what is T of B3 value? 0 comma minus 6. So A is 0, 0 by 4, 4 comma 0 plus minus 6 by 5, 0 comma 5. Okay. Now we need to write the linear transformation, that is a matrix of the linear transformation with respect to two bases. First basis is B1 and second basis is B2. So with the help of that, you have to find the matrix of linear transformation. Okay. Now you can write this as, hence the matrix of T is hence the matrix of T is, we'll write that matrix as this is T from B1 to B2. That is from basis B1 to basis B2. The transformation, that is matrix transformation of T is equals to, so where whatever the quotients are there for this one, those values you have to write here. That is 1 by 4 and this value. This is 0 by 5 means it is 0. So 1 by 4, 0. Next second one, 1 and 2 by 5. That is 1 and 2 by 5. Next this is also 0 minus 6 by 5. Okay. So this is the matrix of the linear transformation. This is how many rows are there? 1, 2. 2 rows are there. How many columns are there? 3 columns are there. And what is the definition given in the starting T definition? It is from 2 to 3. That means 2 rows are there and 3 columns are there. So with the help of that definition of the T and also how it is defined and how the given bases are there, with the help of that we can find a matrix for the linear transformation. Okay. Some example problems are there in your textbook. This is the problem I have told from the exercise. That is a multiple. You see the unit 6. See page number 57. Example 3 is there. That is a very important one. So it is regularly asked, and in check your progress also you have some problems are there. So worked out exercises are also there. That is 66 page number. You have problems with the solutions also. Okay. So practice those all problems. So whatever I have told now, just now problem, no, that is in the page number 70 MEQ question, it is there. That is model examination questions. 6.7.4. So like these questions will be asked for 10 marks. So by this we are completing the block 2. So in block 2 we have seen the about the linear transformation definition, one to one, on to, and epimorphism, homomorphism, isomorphism, and what is the definition of rank, nullity, and what is the range of T, and nullity, null space of T, kernel of T. So in this, these concepts are very important. In fourth unit, even you have the 10 marks theorems are there. And one important theorem, that is a rank nullity theorem, is there no, in unit 5. So that will be even asked for the 20 marks question. Section C will be there, no? So in that also you will get the rank nullity theorem, definition of rank nullity, and also the relation is there, no, between rank nullity. That question is asked in the examination for even 20 marks also, because in the definitions are there, and also theorem is also very lengthy one. So you may get for the 20 marks question also in section C. That is in the page number 44, page number you have definition of what is nullity of T and what is rank of T. And problem theorem proof you have in 44 and 45 page number. So these are the important questions and problems in block 2. Next, if we'll go to the block 3. So block 3 is about the matrix, characteristic values and vectors. So matrices, you have the idea in intermediate. What is the definition of the matrix and what are the order of the matrices? What is column matrix? What is row matrix? And how to find the determinant of the matrix, 2 by 2 determinant, and also the if the given matrix is 2 by 2 or 3 by 3, how you will find the determinant of the matrix, and what is a singular and non-singular matrix. Okay. Non-singular means if the determinant value is not equals to 0, then we call that matrix as a non-singular matrix. So whenever it is a non-singular matrix, we will find the inverse of the matrix. So conditions will be there. So try to just glance on those, what are the definitions of the matrices. So in this problem, in block 3rd, you have about the rank of the matrix, how to find with the help of the converting the given matrix into echelon form or normal form. With the help of that, how you will find the rank of the matrix. And you know about the Gauss elimination method will be there, Gauss Jordan method. With the help of that also we can find the rank of the matrix. So similarly, here with the converting the given matrix into echelon form or normal form, you can find the rank of the matrix. So block 3 is about, so in Gauss Jordan method and also Gauss elimination method, we'll use the elementary transformations. That is converting the R3 rows and columns R3 to R2 by multiplying or by dividing any number, any scalar number here, or with the help of addition or multiplication or division with any number. We can convert the given whatever the values are there given in the rows and columns. We can convert at them and we can find the rank of the matrix. So here we'll have the concept of the elementary transformations. With the help of the elementary transformation, how you will find the rank of the matrix. So that is only the unit 7 elementary transformations. So block 3 is matrix, characteristic values and vectors. In this blocks, unit 7 is elementary transformations. Elementary transformations. So first this in this concept is about the rank we have. How to find the rank of a matrix. So starting in the unit, you have the what is how you'll do the elementary transformations that is given definition in page number 73. Page number 73 you have if A is an m by n matrix, then the determinant of every square submatrix of A is called a minor of matrix. So you know the concept of minor, I think so. So if this is A11, A12, A13, A21, A22, A23, A31, A32, A33. So if this is a matrix, this is the 3 by 3 matrix. Okay. So we can find the determinant of this one. So these are all the elements. How many elements are there? 9 elements are there in this matrix. So we can find the minor. Minor means any 2 by 2 matrix. So you can write A11, A12, A21, A22. And we can find the determinant of this one. And even if you write like this is the minor of the matrix. Like this, you can find the 9 different. So here, this is one minor, this is one minor, and again this is one minor, 3. Okay, these 2 minors. This is 1, this is 2, this is last one. Means minor means it is a 2 by 2 square matrix. 2 by 2 in the sense it is a square matrix. No, if you take any of these 4, and if you find the matrix for this one, any determinant, that is a 2 by 2. From this we can convert the minors of this matrix. Okay. So that only definition is given in the 7.2.1. And regarding of the rank of the matrix, in page number 74 is there. Whenever it is a 3 by 3 matrix, when you find the determinant of this one, if it is, okay, when you find the determinant of this matrix, whenever it is not equals to 0, and it is a square matrix, okay, that means 3 by 3. So then we can say that whatever here the order is there, order of the matrix, that is only rank of matrix. 3. It is 3 by 3. And if you get the determinant value as 0, if it is a square matrix, then the order of rank of that matrix is 3. Okay. So if you get the determinant of A equals to 0, and any minor, okay, any minor value, any one, okay, not all, anyone, if you are getting the, it has not equals to 0, minor of this one. So if you think B, okay, B is one minor, no? So any minor of A, if it is not equals to 0, then rank of A is equals to 2. Okay. So all determinant values, determinant of 3 by 3 matrix, if you are getting it as 0, or in some case you may have 4 by, that is 3 by 4 also. If you have 1, 4, 2, 4, this is 3, 4. So 3 rows are there, 4 columns are there. This is the rectangular matrix. So in this case also, what will happen? For this, we can't find the determinant term. Usually we'll find the determinant whenever it is in the square matrix. Okay. So for this also we can find, but somewhat lengthy process will be there. So you take any of the square matrix, that is 3 by 3 matrix, 1, 2, 3, or 1, 2, 3, or 1, 2, 3, like this, any 3 by 3 matrix you can take. And if you find the determinant of that one, if you are getting those values as 0, then you have to check for the minor of A. Minor of A means only these. This is one minor. This is one minor. This is one minor. So sometimes even minors also you will get 0. So, but all the minors, if you will get 0 means we can't find the. So at least one minor will be there which will be not equals to 0. So if you'll get such minor, then we can write the rank of the matrix as 2. Okay. So for this one condition is that determinant of A should not be equal to 0. So if you're getting 0 means the rank would be 2. If you are not, if you are getting not equals to 0, then rank would be 3. Okay, this is the one method, and another one is finding with the help of the echelon form. Echelon form definition also there in your textbook. Echelon form is nothing but here whatever the elements are there, with the help of elementary transformation, you have to first element of the first row and first column should be 1, and these you have to convert it as 0, 0 like this. So this form is called as a echelon form. Then how many non-zero elements are there? So with the help of that, we can write the rank of the matrix. Non-zero rows. So here 1 is there. This is one non-zero. All are not zero. No? So even in the second row, you have to check if last one element is there, means you have to consider it as a row only. So 1, 2, here all are zeros, no? Then it is the rank of the matrix is 2. That means here whatever the values are given, that values you have to convert like this form. First element should be 1. After that, you have to convert them into zeros. So number of non-zero rows left in the given matrix, that is the number of for the matrix rank. Okay, so that problems also you have in your textbook. So next week we'll see the problems of finding the rank of the matrix by converting it into echelon form. So in page number 75, you have the definition of how to find the elementary transformation. We call it as elementary operations or elementary transformation of a matrix. Either we can do row elementary transformation or else we can do columns, and combining of both elementary transformation of rows and columns also we can do. Okay, so if you are doing rows means we'll represent it as, if it is first row R1, second row R2, third row we'll represent as R3. If columns means it is C1, C2, C3 like this. This whole thing is, this is R1, this is R2, and this is R3, and this is C1, this is C2, C3, and C4. Okay, so by interchanging rows and columns, we can find the rank of matrix. So the definition only, what are the conditions for doing the elementary transformations? Those conditions are given 1, 2, 3. 3 steps will be there. Is how to find the, by multiplying any scalar, or by doing the addition, or by doing the subtraction, by with the help of dividing with the help of any scalar, how to find the linear transformation. That steps are given here. And next to this theorem 75 page number 1, in that only below you have now 7.2.9. This is the very important theorem and almost regularly asked for the, that is a 10 marks questions. So you have even 20 marks question. So you have the chance of getting this question also, because this is a very lengthy theorem you have. If you see the proof, it is almost 2 pages are there. Okay. So whatever the statement is there for this theorem is, elementary transformation do not alter the rank of the matrix. Okay. Whenever you do the elementary transformations for the rank, for finding the rank of the matrix, they will not change the rank of the matrix. Okay. So that is only there. With the help of that, how you are solving, 2 cases will be there. First one is, first case is interchange of a pair of rows does not change the rank of the matrix. So whatever the rank of the matrix will be there, that will be the same whether you do the row transformations or whether you do the column transformation. So it does not show any change in that one. That is about the statement of the matrix. So 2 conditions are, that is 2 cases are taken. First case is, if you interchange the pair of rows or columns, it will not change. And second one is, if you multiplication of the elements of a row by a non-zero number does not change the rank. So 3 we can use. First thing is interchanging of either the second row by first row or first row by third, anything you can interchange. By changing of that also, rank will not change. Or by multiplying, that is R1 into 2 or R1 into 3, like that. If you do any multiplication for the rows or columns, that will also not change the rank of the matrix. That is the second case. And third case is the addition. addition to the elements of a row, the products by any k, means with the help of any scalar k, corresponding elements of any other row does not change the row of the matrix. You can multiply this and you can add this one. At a time you can do three types we can do. First thing is interchanging. Second one is for this only you can do the multiplication. Third one is by multiplying and adding. If you do these three process also, then also the rank of the matrix does not change. That is the important theorem on regarding of this one. So on these problems, we'll see in the next week.